Most architects can name 3 lateral systems, 3 mechanical systems, and 3 insulation strategies. Far fewer can defend which one to pick when you have a high-rise in coastal Florida, a sustainability mandate, and a tight project budget all at once. That gap is exactly where the advanced exam questions live. Foundational work taught you the vocabulary. Advanced work tests whether you can apply it when 2 reasonable answers conflict, and you have to defend the choice. Misread the trade-off, and you fail the exam. Or worse, fail the project. Here are 4 reasons this advanced layer carries the weight the PPD exam gives it. 4 reasons advanced systems work carries this much weight. First, lateral structure is an architectural decision, not just a structural one. Moment frames give you open facades, but cost more steel. Braced frames are efficient, but interrupt the floor plan. Shear walls are cheap, but lock in the planning grid. The exam tests whether you read those architectural consequences before picking. Second, mechanical selection is a ranking problem, not a naming problem. Climate zone, building type, load profile, and energy target each push the answer in a different direction, and the exam wants the option that satisfies the dominant constraint, not just any constraint. Third, continuous insulation and a continuous air barrier are how the wall meets ASHRAE 90.1, and they are also how the assembly survives its first humid summer. Get the layering wrong, and the assembly traps moisture and rots, and the exam tests dew point logic directly. And fourth, net zero strategies, material properties, and fire protection selection all live at the same crossroads. Code says one thing, performance says another, cost says a third. The exam writes from that crossroads on purpose. Here are the 6 advanced subsections in the order the module walks them. Walking the 6 advanced cases. 4.1 compares the 3 primary lateral systems, moment frames, braced frames, and shear walls, and the architectural consequences of each. 4.2 walks mechanical system selection criteria as a ranked list, climate zone, then load profile, then building type, then energy target. 4.3 covers continuous insulation and continuous air barriers as the envelope's path to ASHRAE 90.1 compliance, and as the moisture management story that keeps the wall assembly intact. 4.4 is net zero energy and carbon strategy, passive design, electrification, on-site renewables, and the offset hierarchy. 4.5 reviews the material properties, thermal conductivity, density, modulus of elasticity, vapor permeance, that engineers assume the architect knows. And 4.6 walks, fire protection selection, sprinklers per NFPA 13, standpipes per NFPA 14, and alarm systems per NFPA 72, with the IBC thresholds that trigger each. One posture shift before we step into section 4.1. 4 things to hold in mind. First, advanced systems questions reward ranking. The prompt always buries the dominant constraint in a single sentence, and your job is to find it and let it pick the answer. Second, every structural and mechanical decision has architectural consequences. Facade rhythm, ceiling height, column-free spans, ductwork space, and the exam reads those consequences as the criteria, not as afterthoughts. Third, the energy code, the fire code, and the accessibility code can disagree on the same wall assembly, and when they do, the stricter rule controls. The exam writes those conflicts on purpose. And fourth, net zero is a hierarchy, not a list. Reduce demand first through passive design and envelope, then electrify the loads that remain, then offset what you cannot eliminate. Skipping a step makes the strategy more expensive than it needs to be. With that posture set, we step into section 4.1. Every building you will ever design has to fight horizontal forces. Wind pushes on the broadside, earthquakes shake the ground underneath, and if there is nothing holding the structure together against those loads, the building tips, rotates, or collapses, injuring occupants. The lateral force resisting system, the LFRS, is the structural backbone that absorbs that fight. And the choice you make as the architect drives three things that the exam will hit you on. It drives floor plan flexibility, because shear walls and braces eat openings that moment frames don't. It drives construction cost, because moment connections are expensive in ways shear walls are not. And it drives seismic performance, because ductility, the ability to deform without breaking, varies dramatically by system. Pick wrong, and you spend the next 2 months in design development trying to negotiate window openings back into a wall that the structural engineer needs solid. Let's put the three primary systems side by side and see how they actually behave under load. 4 systems, 4 very different conversations with your client. The moment frame is the architect's friend. Rigid beam-to-column connections resist rotation. No diagonal brace cuts across the bay, and you get the most open floor plan that structural engineering permits. The trade-off shows up in cost because every one of those rigid connections is a heavy, expensive piece of fabrication. Steel special moment frames also carry high ductility, which is what allows them to survive a big earthquake by absorbing energy through controlled deformation. The braced frame solves the cost problem by replacing rigid connections with diagonal members that take load in straight tension and compression. But those diagonals occupy a bay, meaning that bay can't hold a window or a doorway in the obvious place. Ductility is moderate, not high. Shear walls are the cheapest lateral system you can specify because a wall is much simpler to build than a connection or a brace. But a shear wall is by definition a wall. You cannot punch openings through it without paying for headers, jams, and reanalysis. Ductility ranges from very low for unreinforced masonry to very high for specially detailed reinforced concrete. The dual system combines a moment frame with shear walls to get redundancy, which is what the code rewards in high seismic zones. But you're paying for both systems at once. Braced frames have their own internal taxonomy, and the exam likes to test which type fits which seismic demand. 3 braced frame configurations, ordered from simplest to highest performing. The concentrically braced frame is the default. Diagonals meet at beam column joints. The frame is economical to fabricate, and the brace resists both compression and tension. The catch is that when a steel brace buckles in compression during an earthquake, it loses most of its capacity, so ductility is only moderate. The eccentrically braced frame moves the diagonal off the joint, creating a short link beam between the brace and the column. That link beam is designed to yield first, acting as a structural fuse that absorbs energy while protecting the brace and the columns. Ductility goes up because the fuse mechanism is predictable and repairable. The buckling restrained braced frame is the high-performance option. The brace core is wrapped in a sleeve that prevents it from buckling in compression, so the brace can yield in both directions and dissipate enormous amounts of energy. BRBFs are what you specify for hospitals and emergency facilities in California, where the building has to stay operational after the design earthquake. Walk away with the 3 trade-offs that decide which system fits a given project. 5 takeaways from the lateral system comparison. There are 3 primary lateral force resisting systems: the moment frame, the braced frame, and the shear wall, plus dual systems that combine 2 of them for redundancy in high seismic zones. Moment frames buy you the most architectural freedom because nothing cuts across the bay, but you pay for that freedom in expensive, rigid connections. Shear walls are the cheapest system to build, but they constrain your plan because openings cost detailing. Ductility, the ability to deform without breaking, matters as much as strength once seismic demand climbs, and it is the factor that drives system choice from California up. Braced frames are not one thing. They climb from concentric, the default, through eccentric with its energy-dissipating link beam, up to buckling restrained, which yields in both directions and is what hospitals and emergency facilities specify. And the exam is going to test your ability to read a project description. weighing floor plan, cost target, seismic zone, and occupancy. Then pick the lateral system that actually fits. Most architects panic at the seismic chapter of ASCE 7. They see the equations, the response modification factors, and the design category letters, and they assume it's an engineering problem they can leave to the structural consultant. That mindset is what causes failed buildings, occupant injuries, and failed exam questions. The seismic design category, or SDC, is the code's way of classifying every building project by its actual seismic risk, based on three things: where the site is, what soil sits underneath, and how important the building is to public safety. That category then decides which structural systems the code will permit on your project, and how much detailing the structural engineer will be forced to include. Get the category wrong, and your architectural concept disappears under shear wall infill that wasn't in the schematic, while you absorb the cost of a redesign. Get it right, and you can defend the design when the structural engineer comes back asking for changes. 6 categories, A through F, and each one redraws what you're allowed to build. SDC A through F maps the entire country and every occupancy type. Category A covers very low seismicity sites in the central United States, where the code lets you specify almost anything. B and C step up through low and moderate risk. Most of the eastern half of the country and the Pacific Northwest land here, with modest height limits and some detailing requirements. D is where it gets serious. Most of California sits in SDCD, and at this level, the code starts removing systems from your menu and demanding special detailing on what's left. Ordinary moment frames are not allowed. You need intermediate or special detailing for any moment-resisting frame. Category E is reserved for very high-risk sites near major faults, where only the most ductile systems, special moment frames, BRBFs, special reinforced concrete shear walls, are permitted, and even those require enhanced connection design. Category F adds essential facility rules on top of E, which applies to hospitals, fire stations, and emergency operation centers. If your building has to remain functional after the design earthquake, meaning patients can still be treated and ambulances can still leave, you are in F territory, and you cannot value engineer your way out of the detailing. Inside each category, a handful of code variables decide how much force the structure actually has to carry. 5 variables decide how much seismic force your building actually has to carry. The response modification factor, R, is the most counterintuitive. A higher R means a more ductile system, which means lower design forces, not higher. That trips up architects and exam candidates every year. The reason is that ductile systems can absorb energy through controlled yielding instead of resisting it elastically. So the code lets you design for a fraction of the actual demand if you commit to the detailing that delivers the ductility. Special moment frames sit at R equals 8, the highest available, which is why they show up in major California projects despite the cost. Ordinary moment frames sit at R equals 3 to 3.5, much higher design forces, much simpler connections, and they are not allowed in SDCD and above. Base shear 5 is the total lateral force at the building base, computed from building weight, fundamental period, soil class, and R. The importance factor, i.e., multiplies the design force when the occupancy demands it. A regular office is IE equals 1.0. An essential hospital is IE equals 1.5. That 50% increase is what protects the building owner from a code-compliant building that still cannot operate after the quake. Lock these 5 takeaways and you can read a seismic worksheet without flinching. 5 takeaways on seismic design categories. SDC runs A through F and classifies every building by site seismicity, soil class, and occupancy importance, with F reserved for essential facilities near faults. Higher categories take systems off your menu and demand more detailing on the ones that remain. Ordinary moment frames disappear above SDCC, and only special detailing survives near major faults. R is the response modification factor. And the rule that catches the most exam takers is that a higher R means a lower design force, because the code rewards ductile systems that can absorb energy through controlled yielding. The trade-off is that those high R systems require special detailing that drives connection cost up. So you save on member sizes, but you spend on fabrication and inspection. Ordinary moment frames are banned at SDCD and above because their R of 3 is not enough to justify the simpler connections under high seismic demand. And essential facility occupancies, hospitals, fire stations, emergency operations centers, carry an importance factor of 1.5, which means a 50% increase in design force on top of everything else. Here's the uncomfortable truth about wind. It doesn't load a building uniformly. Architects think of wind as a single horizontal push, but ASCE 7 treats it as 5 distinct loadings on 5 distinct surfaces, plus an internal pressure that depends on whether your envelope holds tight or breaches. Roof corners experience 2 to 3 times the pressure of the roof field, which is why every post-hurricane forensic report you'll ever read starts at the corner of the roof and works inward. The architect who specifies the same fastener spacing across the entire roof deck is the architect whose building loses its roof in a Category 3 hurricane, injuring occupants, and personal liability follows when the failure is traced to a designer who ignored ASCE 7. Wind design is not a single number. It is a map of pressures, and the corners and edges always carry the highest demand. Before we map the pressures, you need the 2 acronym vocabulary the structural engineer will use on every wind call: M, W, F, R, S, and C, and C. 2 systems, 2 completely different load values, and both apply simultaneously to the same building. The main wind force resisting system, MWFRS, designs the overall structure for the total lateral wind load: the frame, the shear walls, the floor diaphragms, the lateral force resisting members that keep the building from sliding sideways. Components and cladding, C&C, designs the individual elements that catch local peak gusts: the windows, the roof panels, the soffits, the door assemblies. C&C pressures are higher, often significantly higher, because a small area exposed for a short time can experience peak gusts that the larger MWFRS calculation averages out across the entire building face. The architect controls which is which when they specify the building envelope. Get the glazing right, and the building stays enclosed, keeping internal pressure low. Let one window breach, and the building flips to partially enclosed, and every interior surface picks up an outward push that doubles your design pressures. Now see how those pressures actually distribute across the building? 5 surfaces, 5 very different stories. The windward wall receives positive pressure pushing inward. This is the load the lay reader pictures when they hear the word wind. The leeward wall, the sidewalls, and most roofs experience negative pressure, also called suction, pulling outward. That suction is what tears cladding off buildings and lifts roof decks during storms, because every fastener that holds a panel down has to overcome the suction on the area it tributaries. Flat and low-slope roofs see uplift across their entire surface, and at the edges and corners, that uplift doubles or triples. Those are the failure initiation zones in every hurricane forensic report. The one exception to the suction rule is a steep windward roof slope above 30 degrees, where the wind hits the slope nearly head-on and creates positive pressure pushing inward and down. Your rafters in that case carry the wind load like an additional dead load. Below 30 degrees, even the windward roof slope is in suction. 6 variables drive what those pressures actually compute to for any given project. 6 variables drive every wind calculation on your project. Basic wind speed comes off the ASCE 7 maps in miles per hour, expressed as a 3-second peak gust at the site. Exposure category captures the surrounding terrain. Exposure B for urban and suburban with plenty of building obstruction. C for open terrain like flat farmland, and D for coastal sites and flat shoreline, which drives design forces highest because nothing slows the wind down before it hits your building. Topographic factor KZT accelerates wind over hills, ridges, and escarpments. A building sitting on top of a coastal bluff sees significantly higher pressures than the same building at the base. Internal pressure depends on enclosure classification. An enclosed building is the easy case. A partially enclosed building doubles the internal pressure assumption, and an open structure like a stadium roof is its own analysis. CNC pressures spike at corners and edges to 2 or 3 times the field value, which is why the roof edge always uses tighter fastener spacing than the field. And the MWFRS calculation handles the overall lateral load on the structural frame. That's the number the structural engineer needs to size the lateral system. Walk away with the 5 wind facts that protect both the building and your design intent. 5 takeaways on wind loads. Wind is not a uniform horizontal push. It splits into positive pressure on the windward wall, negative pressure on the leeward and side walls, and uplift on most roofs. Roof corners and edges experience 2 to 3 times the pressure of the roof field, which is why hurricane failures start there and work inward, and why the architect specifies tighter fastener spacing at perimeter zones. MWFRS sizes the overall structural frame for total lateral wind load, while CNC sizes individual cladding elements for short-duration peak gusts, and both calculations apply to the same building simultaneously. Exposure D coastal sites, combined with a partially enclosed building envelope drive, design forces highest, which is why impact-resistant glazing matters in hurricane regions. Keep the envelope enclosed, and your internal pressure assumption stays manageable. Let one window breach during a storm, and the building flips to partially enclosed, doubling the outward push on every interior surface. And that's when the roof leaves the building. Every architect has the same conversation with the structural engineer in design development. You drew an open ground floor retail under a 5-story residential, and you drew an L-shaped plan because the site demanded it. And now the structural engineer is asking for a moment frame at the ground floor and a seismic joint between the L volumes. The architect feels ambushed. The engineer is exasperated. Neither party is wrong. The building has irregularities, and irregularities are the code's word for plans that don't distribute lateral forces cleanly. Address them early in schematic design, and they're cheap. Wait until DD, and they cost real money in transfer beams, added bracing, and lost program. Soft story failures kill people in earthquakes. The famous photos of pancaked Northridge apartment buildings all show parking garages at grade with stiff walls stacked above. Diaphragms, the floors and roofs themselves, are what tie the building together and deliver lateral forces to the LFRS. And the choice of diaphragm type changes how those forces distribute. Start with the 3 diaphragm types and how each one allocates load. 3 diaphragm types and 3 different ways your lateral forces will distribute. A rigid diaphragm. A concrete slab or a concrete-topped metal deck is stiff enough in plane that it forces the vertical resisting elements to share load in proportion to their relative stiffness. A stiffer shear wall attracts more force. A flexible braced bay attracts less. A flexible diaphragm, wood sheathing, or an untopped metal deck deforms in plane like a deep simple span beam and distributes lateral forces by tributary area instead, regardless of the stiffness of the vertical elements below. Each line of resistance picks up the load that falls into its tributary width. A semi-rigid diaphragm sits between the two. Thin concrete fill on metal deck is the classic example, and it requires explicit analysis to determine which way the forces actually flow. Architectural consequence. If you cut a large atrium opening through a rigid diaphragm, you have just disrupted the load path, and the structural engineer will need to add a cord, a collector, or both to carry forces around the opening. Beyond diaphragms, ASCE 7 calls out 5 plan and section irregularities that trigger penalty factors and special detailing. 5 irregularities ASCE 7 calls out, each one converting an architectural choice into a structural penalty. The soft story is the most dangerous vertical irregularity. A single story that is significantly less stiff than the story above will concentrate the entire lateral drift of the building at that level, and during a strong earthquake, it often collapses. The classic example is a parking garage at grade under stacked residential floors above. Northridge in 1994 killed dozens of people in soft story failures. Torsional irregularity happens when the center of rigidity is offset from the center of mass. So when lateral force pushes the building, it doesn't just translate, it also twists, overloading the lines of resistance on the far side. Reentrant corners in L, T, U, or cruciform plans concentrate stress at the inside corner. A small relative motion between the two wings cracks the concrete or fractures the steel at the intersection. Diaphragm discontinuities from large openings, atriums, or split-level floors disrupt the load path and force cords and collectors around the breach. And weight irregularity. One floor that's much heavier than the floors around it, like a mechanical penthouse, concentrates seismic forces at that level because seismic load scales directly with mass. Most irregularities trace back to a small list of architectural decisions you can spot in schematic design. 5 architectural decisions account for almost every irregularity that lands on a project. Open ground floor retail, or parking under residential above, creates the soft story condition that has killed more people in earthquakes than any other lateral defect. The fix is a moment frame, a continuous shear wall, or a brace at the ground floor that ties the upper stiffness down to the foundation. Cantilevered upper floors or setbacks change mass and stiffness vertically, which the code penalizes through additional analysis and increased detailing. L, T, U, or cruciform plan shapes create re-entrant corners at the inside angles where the two wings meet, and either you reinforce that corner heavily or you split the building into separate rectangles with a seismic joint. Atriums, large stair openings, and split-level floors create diaphragm discontinuities that require collector elements to carry forces around the breach. And concentrating heavy mechanical equipment on one side of the roof, a penthouse on the east end, for instance, moves the center of mass away from the center of rigidity and produces torsion. Every one of these is a schematic design decision, and the cheapest fix is always made before structural drawings start. Carry these 5 takeaways into every project review. 5 takeaways on diaphragms and irregularities. Diaphragms come in 3 flavors, and the type drives force distribution. Rigid, concrete slabs send forces to vertical elements in proportion to stiffness. Flexible wood or bare metal deck diaphragms send forces by tributary width, regardless of stiffness. And semi-rigid systems need explicit analysis. The soft story is the deadliest vertical irregularity by a wide margin, and the classic case, open parking under stacked residential, has been responsible for collapse and fatalities in every major U.S. earthquake. Reentrant corners in L, T, U, or cruciform plans concentrate stress at the inside angle, and the architect either reinforces that corner heavily or splits the building into separate rectangles with a seismic joint. Atriums, large stair openings, and other diaphragm discontinuities cut the floor membrane and force the structural engineer to add cords and collectors to carry lateral loads around the breach. And the discipline that protects both your design intent and your fee is to spot these irregularities in schematic design when fixes are cheap and architecturally invisible. By DD, the cost and the visual penalty compound. Every architect who has been ambushed by a mechanical engineer in design development knows the same painful truth. HVAC selection looks like an engineering problem, but the moment the engineer needs more shaft space or a deeper ceiling plenum, it becomes your problem. The architect doesn't size the chiller, but the architect absolutely commits the shaft, the plenum, the roof real estate, and the mechanical room footprint. Get the system wrong in schematic, and you fail the building program. There's no room for the equipment by DD, the owner files lawsuits over the redesign cost, and the architect ends up personally liable on a claim the insurer will not defend cleanly. There is no universally best HVAC system. The right answer depends on building type, size, climate zone, budget, and the owner's priorities for energy, comfort, indoor air quality, and acoustics. The exam will hand you a program and ask you to pick the system that fits. Start with 7 common building types and the systems that suit each one. 6 building types and the system families that fit each one. Large offices land on VAV, variable air volume, with a central plant because tenant fit-outs reconfigure zones every few years and VAV adapts. Small offices skip the central plant and pick packaged rooftop units or VRF because the first cost premium of a central plant isn't recovered on a smaller footprint. Hotels need individual room control with quiet operation. Fan coils, PTACs, and VRF all work, and most large hotels run simultaneous heating and cooling on opposite faces of the building, which favors VRF's heat recovery capability. Hospitals demand VAV with 100% outside air, a robust central plant, strict pressure relationships between rooms, and redundancy that lets the building survive a chiller failure without losing infection control. Schools need indoor air quality, acoustic separation, and maintenance simplicity. VAV, unit ventilators, and VRF all show up depending on the budget. Laboratories are dominated by fume hood exhaust, which drives the entire HVAC design. You size everything else around the hood requirements, and then add energy recovery to claw back what the exhaust loses. 5 additional drivers cut across all building types and decide which family is actually right. 5 drivers cut across the building type matrix and decide the system family in practice. First, cost versus operating cost is the budget conversation. A central plant with chilled water costs more in capital, but less to run over a 30-year life, while packaged rooftops are cheap to install, but expensive to operate at scale. Flexibility for future reconfiguration favors VAV and VRF, both of which let you rezone with minor terminal changes. Constant volume systems lock the zoning in concrete. Noise sensitivity rules out anything with an air handler near the occupied space. Hotels and theaters typically specify fan coils, hydronic radiant, or VRF because the noise sources sit in mechanical rooms or in the ceiling space outside the room. Redundancy is the hospital and data center requirement. Dual chillers, dual pumps, multiple distribution paths, and a generator that keeps the central plant alive through utility outages. And ceiling space is the most direct architectural impact. Overhead ductwork needs 12 to 18 inches of clear depth. VRF refrigerant piping and fan coils need much less. And the floor-to-floor height the architect commits in schematic locks in or rules out entire system families. Lock these 5 takeaways before the next mechanical coordination meeting. 5 takeaways on mechanical system selection. There is no universally best HVAC system. The right answer falls out of building type, size, climate, budget, and what the owner cares about. And that's the question the exam will hand you. Hospitals demand a specific combination: VAV with 100% outside air, strict pressure relationships, central plant redundancy, and continuous infection control commissioning, and none of those requirements are negotiable. Hotels and other quiet room programs favor VRF or fan coils because the equipment can sit outside the occupied space and individual room control is built into the system architecture. The architect does not size the equipment, but the architect absolutely commits the floor-to-floor height, the ceiling plenum, the shaft, and the mechanical room space the equipment needs. Getting those commitments wrong in schematic causes the most expensive late design changes on any project. The most common architectural HVAC failure is insufficient ceiling depth. You locked the floor-to-floor at 12 feet to save curtain wall cost, and now the VRF head crashes the suspended ceiling layout. Overhead ductwork is the default distribution method in U.S. construction, and the default is fine for 90% of projects. The other 10% are the ones the exam asks about. Underfloor air distribution moves the supply ductwork into a raised floor plenum and lets you punch floor diffusers wherever the tenant wants them. Active and passive chilled beams replace bulk ducted supply with a coil in the ceiling that does most of the cooling work locally. Both options reduce overhead ducting dramatically. Both improve indoor air quality, and both come with traps that have buried real projects in litigation. Get the dew point wrong on a chilled beam, and you'll be sued by the owner the first time condensate drips onto a finished floor. Get the plenum leakage wrong on UFAD, and the system never balances. The architect commits the floor-to-floor height that makes either option possible. Get that decision wrong in schematic, and the mechanical engineer has nothing to work with. 4 alternative air distribution families, and what each one really gives up. 4 alternatives to overhead ducting, ordered by how aggressively they remove ductwork from the ceiling. Underfloor air distribution pressurizes the raised floor plenum to roughly 0.05 of an inch of water column, and floor diffusers let occupants modulate their own comfort. The plenum leaks at every floor penetration and partition base, unless you specify continuous gasketing, and floor-to-floor height grows by the depth of the raised floor. Displacement ventilation supplies cool air at low velocity near the floor, lets it stratify naturally as occupants warm it, and gives you excellent indoor air quality because contaminants rise away from the breathing zone. The catch is cooling capacity. The displacement strategy only works for moderate sensible loads. Active chilled beams induce room air across a chilled water coil in the ceiling, cutting ductwork by 60% and running silently, but the primary air has to dehumidify the space because the chilled water coil cannot handle moisture. Passive chilled beams have no primary air at all and rely on natural convection, so capacity is very low and they cannot ventilate the space. Pair them with a dedicated outdoor air system or skip them. All 4 systems share the same architectural coordination demands that the architect has to commit to in schematic. 5 coordination commitments that the architect locks in long before the mechanical engineer finishes sizing equipment. Mechanical room area runs 4 to 9% of gross building area for buildings with central plants. Try to take that back at schematic design freeze, and you lose the project. Vertical shafts have to land near the building core so that duct, pipe, and electrical risers can reach every floor without obstructing leasable area. Misplaced shafts force horizontal runs that eat the ceiling plenum. Speaking of which, the ceiling plenum needs 18 to 30 inches of clear depth for the full stack of duct, pipe, conduit, sprinklers, and structural deflection. Commit 12 and you'll be hand routing every system in coordination meetings. Equipment access clearances around air handling units, boilers, and chillers are code mandated and non-negotiable. The inspector will not certify the building if a tech can't get to a panel. And BIM clash detection happens in design development, not construction. Finding a duct running through a beam during construction is what triggers change orders, schedule slips, and the lawsuits that destroy a project budget. Lock 4 takeaways before the next mechanical coordination meeting. 5 takeaways from advanced air distribution. Underfloor air distribution buys you tenant-tunable comfort and better indoor air quality, but you pay for it in extra floor-to-floor height and in the constant risk of plenum leakage at every floor penetration. Active chilled beams cut ductwork by roughly 60% and run quietly, but the coil cannot handle moisture. You must pair the system with a dedicated outdoor air system that dehumidifies the ventilation air before it reaches the room. Passive chilled beams have very low cooling capacity and no ventilation function, so they only work as a supplement to a primary system. Condensation on chilled beam coils in humid climates is a documented design failure that gets the architect personally liable in court. Get the dew point analysis wrong in design development, and you're explaining yourself to an attorney. And the architect commits floor-to-floor height, shaft location, and ceiling plenum depth in schematic design. Every MEP coordination decision that follows depends on those three numbers being right. Most architects treat commissioning as a line item the owner pays for and the mechanical contractor handles. That's the misread. Commissioning, abbreviated C-X, is the quality assurance process that verifies the building systems are designed, installed, started up, and operating in line with the owner's stated requirements. And it is the single best defense against the lawsuits architects face when the building doesn't perform after occupancy. The LEED rating system requires fundamental commissioning as a prerequisite. The IBC and energy codes increasingly mandate it, and every owner you'll work with on a serious project will demand it on paper. The architect's job is to scope it correctly, hire the commissioning authority on the right schedule, and verify the work was done. Skip that oversight, and you've stamped a building whose mechanical performance you cannot defend in court. The process runs across 5 phases, beginning before design starts. 5 phases, and the sequence matters because each phase produces a deliverable that the next one verifies. Pre-design is where the owner's project requirements, the OPR, get written down and the commissioning authority gets hired. Designing without an OPR is designing without a target, and the exam will test whether you know to put the owner on the hook for stating their requirements in writing. Design phase is where the commissioning authority reviews the developing documents against the OPR. The mechanical engineer produces the basis of design, and the CX authority red pens the specifications. Construction is where submittals get reviewed, installation gets verified against documents, and equipment startup is witnessed by someone who is not the installer. Functional testing happens after substantial completion. Every system is exercised in every operating mode the design contemplated. And the occupancy phase runs 10 to 12 months, covering seasonal performance testing and operator training, because a building that performs in summer can still fail in winter. LEED splits commissioning into a fundamental tier you must hit and an enhanced tier you earn credit for. LEED splits commissioning into 2 tiers that have very different cost and rigor profiles. Fundamental commissioning is the prerequisite. You cannot certify any LEED project without it. The scope covers HVAC, controls, and domestic hot water. The commissioning authority can be a member of your design team as long as they're independent of the design discipline being checked. Warranty testing covers a single season, and permanent monitoring is not required. Fundamental CX is what most projects opt for, and it satisfies the increasingly common code mandate. Enhanced commissioning is the credit tier, and it raises the bar in 4 directions at once. The scope expands to every energy and water system in the building, plus the envelope assemblies. The commissioning authority must be independent of both the design team and the construction team, meaning you hire a true third party. Permanent energy monitoring becomes mandatory, and warranty testing extends across all 4 seasons over 10 months or more. Pick fundamental when the owner is rate conscious. Pick enhanced when the owner intends to hold someone personally liable if the energy bills aren't what the model promised. Lock 4 takeaways before the next LEED scoping meeting. 5 takeaways from commissioning. The process runs 5 phases: pre-design, design, construction, functional testing, and a 10 to 12-month occupancy phase. And it is the only systematic mechanism that catches mechanical errors before the building's lifetime energy use locks in. Studies show that commissioning identifies deficiencies in nearly every building tested. Energy savings from correcting them run 5 to 15%, and the median cost of commissioning is paid back in less than 5 years from energy savings alone. LEED fundamental commissioning is the prerequisite that gates every certification. It covers HVAC, controls, and domestic hot water with a CX authority independent of design. Enhanced commissioning is the credit tier that expands scope to envelope, makes the authority independent of both design and construction, and adds permanent energy monitoring with a year-long warranty. And the entire process depends on a written owner's project requirements document. Without an OPR, you have no target, no verification criteria, and no defense if the building underperforms in court. The single most expensive architectural decision on most projects is the floor-to-floor height committed in schematic design. Get it right, and the mechanical, electrical, and plumbing trades fit cleanly inside the plenum, the structural depth, and the shafts you allocated. Get it wrong, and design development becomes a 6-month negotiation where every trade is trying to steal an inch from the trade next door. The architect cannot recover the dimension in DD. Beams, ducts, sprinklers, conduit, lights, and structural deflection all compete for a fixed depth, and lowering the floor-to-floor after schematic means redesigning the structure. Most of the lawsuits and change orders that destroy project budgets trace back to this one commitment. Run a coordinated section through the deepest condition, usually the duct branching nearest the air handling unit room, before structural depth is sized, and lock the dimension before you leave schematic. 6 space allocations the architect has to commit to before the engineers can do their work. 6 space allocations the architect commits in schematic, and the cost of getting any of them wrong runs from change orders into the lawsuits that destroy careers. The main mechanical room takes 4 to 9% of gross floor area, sits at grade or in the basement so trucks can replace equipment over the building's life, and is non-negotiable. Designers who try to recover the area in design development always lose. Electrical rooms run 1 to 2%, sit centrally to minimize distribution runs, and must stay dry. Putting electrical under a wet pipe is the kind of detail that gets the architect personally liable when the panel floods. Telecom and data closets stack 1 per floor with a main entry room, climate-controlled, with no water above. Rooftop equipment requires structural support, acoustic and visual screening, and maintenance access. The neighbor noise complaint is a recurring real-world problem. Ceiling plenums need 18 to 36 inches for the full stack of structure, duct, pipe, sprinkler, conduit, and lights. And vertical shafts run 2 to 4% per floor, sit adjacent to the building core, and must be continuous floor to floor with a fire-rated enclosure. Discontinuous shafts mean horizontal runs that eat the ceiling plenum. 7 coordination failures repeat on project after project, the architect's checklist for design development. 7 coordination failures that surface on project after project, ranked roughly by how often they cost real money. Number 1 is insufficient floor-to-floor height for ductwork at beam intersections. The duct hits the beam and the trades start sniping. Number 2 is a mechanical room too small to fit the equipment, plus the code-mandated maintenance clearances around it. The inspector will not certify the building until you can prove a technician can reach every panel. Number 3 is the electrical room located where water pipes run overhead. The first time a pipe leaks, the panel floods, the building loses power, and the architect gets sued. Number 4 is no future replacement pathway for chillers and big air handling units. Walls built around equipment mean the next owner has to demolish to replace, which is a documented basis for professional negligence claims. Number 5 is shafts, sized for today's loads with no headroom for future HVAC expansion. Most owners increase load over the building's life. Number 6 is fire dampers that fight with the duct routing and stop the install. And number 7 is plumbing waste lines that conflict with structural beams. Running the waste is harder than rerouting the duct, and the late-stage redesign is the most expensive change order on the job. Lock 4 takeaways before the next schematic design freeze. 5 takeaways from MEP space planning. Floor-to-floor height is the single most expensive architectural decision you make in schematic, and the trade-offs you locked in there cascade through every coordination meeting that follows for the rest of the project. Mechanical rooms run 4 to 9% of gross floor area. Electrical rooms run 1 to 2%. Vertical shafts consume 2 to 4% per floor. Insufficient ceiling plenum depth for ductwork is the most cited MEP coordination failure in the post-project literature, and it traces directly back to that schematic design dimension. Future replacement pathways for chillers, boilers, and air handling units are non-negotiable. Building a wall around equipment that has a 30-year replacement cycle is the kind of error that ends up in a deposition. And the operational defense is to run a coordinated section through the deepest condition before the structural engineer sizes the beams, lock the floor-to-floor in writing, and refuse to revisit it after schematic design freeze. Most architects underestimate how unforgiving the modern envelope code has become. High-performance envelopes rely on 2 continuous layers that you detail, the contractor installs, and the inspector verifies. Continuous insulation, abbreviated CI, eliminates the thermal bridges that turn every stud, every shelf angle, and every parapet into a heat leak. The continuous air barrier prevents uncontrolled air leakage that drives moisture into the wall cavity and steals 15 to 40% of the building's HVAC energy. Both layers have to run unbroken across the entire enclosure. Every window jamb, every roof penetration, every floor-to-wall transition is a chance to defeat the system. The Energy Code now mandates whole building air leakage testing for many occupancies, and failing that test after substantial completion means the architect has to redesign while the owner files lawsuits over the remediation cost. The detail you draw at the parapet decides whether the building passes the test or doesn't. ASHRAE 90.1 sets continuous insulation minimums by climate zone. Here are 4 representative zones. Continuous insulation minimums climb steeply as climate zone moves from hot to cold. And the steel frame numbers show why thermal bridge mitigation matters so much. In Climate Zone 1, which is very hot, the steel frame wall can satisfy the code with no continuous insulation at all, because the thermal bridge through the studs is not punishing enough to fail compliance. In Climate Zone 3, warm, the code requires R7.5 continuous outside the sheathing on a steel frame wall, which is roughly 1.5 inches of rigid foam. In Climate Zone 5, cool, you add an R13 cavity bat to that same R7.5 continuous layer, and on a mass wall, the continuous requirement jumps to R11.4 because the mass wall thermal bridge penalty is different. In Climate Zone 7, very cold, the steel frame total climbs to R7.5 continuous plus R19 in the cavity, and the roof requirement reaches R35 above deck. Specify the wrong thickness in any zone, and the building fails the prescriptive path. You'll end up justifying the performance path through energy modeling that costs the project both schedule and budget. Air barriers have 3 nested thresholds: material, assembly, and whole building. Air barrier performance is verified at 3 nested levels: material, assembly, and whole building. And the architect's specification has to satisfy all 3. At the material level, the standard requires less than 0.004 of a cubic foot per minute per square foot of leakage at 1.57 pounds per square foot pressure. That is, a laboratory test on the sheet material itself, run before it ever reaches the project. At the assembly level, the same test method is applied to the joints, transitions, and seams between materials. The threshold widens to 0.04 because field joints leak more than continuous material. The whole building threshold, which a growing number of jurisdictions require, is less than 0.4 of a cubic foot per minute per square foot at the same test pressure. That is, a blower door test on the completed building, and a failed result triggers remediation that the architect ends up defending in court. The IECC accepts either the whole building test or a thorough visual inspection of the installation, depending on jurisdiction. The project specifications must say which path the project is taking. Lock 4 takeaways before the next envelope coordination meeting. 5 takeaways from continuous insulation and air barriers. The high-performance envelope is defined by 2 layers that have to run continuous across the entire building. Break either one at a parapet, jam, or floor line, and the envelope fails. ASHRAE 90.1 continuous insulation minimums climb from no CI in Climate Zone 1 to R15.2 on a mass wall in Climate Zone 7, and the steel frame thresholds tighten in parallel because thermal bridging through studs is a major loss path. Air barrier compliance is verified at 3 levels: material, assembly, and whole building, and the project specification has to spec all 3. Air leakage drives 25 to 40% of HVAC energy in poorly detailed buildings, which is why energy codes have moved to blower door testing for entire categories of construction. And a failed whole building test after substantial completion is the kind of result that triggers remediation lawsuits. Get the parapet detail wrong, and you are the one personally liable for fixing it. Every architect designing a building taller than 3 stories will eventually specify a curtain wall, and most architects underestimate what the choice actually commits. Curtain walls hang from the structure, span floor to floor, manage water through pressure equalization and weeped flashings, accommodate seismic and wind drift through deliberate flexibility in the mullions, and have to survive the racking test in AAMA 501.4 without breaking a single piece of glass. The architect picks the system type in schematic: stick, unitized, point-supported, or double skin, and that choice locks in cost, schedule, fabrication complexity, and water management strategy for the rest of the project. Pick the wrong system for the building's height and exposure, and you'll be defending the leak that develops in year 3, with the owner's attorney asking why you didn't specify pressure-equalized detailing the climate clearly required. The most reliable water management strategy has its own technical name and deserves a moment of attention. Pressure equalization is the single most important water management concept in modern curtain walls. The principle is simple. Water gets driven through joints not by gravity, but by pressure differential. Wind hits the outboard face, creates a higher pressure outside than inside the cavity, and pushes water through every joint that isn't perfectly sealed. The pressure-equalized rain screen ventilates the cavity directly to the outdoors, so the pressure inside the cavity matches the pressure outside. With no differential, there's no driving force, and the gaskets only have to manage the small fraction of water that runs across the surface. Combine the equalized cavity with a sealed backup wall and weeped flashings that drain any water that does get in, and you have the most reliable water management strategy that the industry has produced. The alternative, face-sealed curtain wall, assumes the outermost face is perfectly waterproof, which it never is over a 30-year service life, and the lawsuits that follow the leaks confirm it. 4 curtain wall types fight different battles with cost, schedule, and aesthetics. 4 curtain wall types and the project conditions each one fits. Stick systems assemble piece by piece in the field. Mullions, transoms, glazing, gaskets, and they trade installation speed for geometric flexibility. The stick system is what you specify when the building has a complex curved or faceted geometry that fabricated panels would never accommodate. The trade-off is field labor, weather dependency, and a much slower schedule than the unitized alternative. Unitized systems prefabricate complete panels in a controlled factory, ship them to the site, and crane them into place. Quality control is dramatically better because the gaskets are installed indoors. Schedule speeds up because crews are not sequencing field assembly, and the system dominates high-rise construction in U.S. markets. Point-supported glass uses spider fittings at the corners of each pane, eliminates mullions entirely, and creates the most dramatic transparent walls in commercial architecture. It is expensive, the engineering is complex, and insulation values are limited by the glass thickness alone. Double-skin facades use 2 layers of glass with a ventilated cavity between, and they offer excellent acoustics and natural ventilation possibilities. but at very high cost and with maintenance issues in the cavity that get the architect personally liable when the cleaning crew can't safely reach the inside face. Lock 4 takeaways before specifying curtain wall on the next high-rise. 5 takeaways from curtain wall design. The most reliable water management strategy for tall buildings is the pressure-equalized rain screen, which ventilates the cavity behind the cladding to the outdoors and eliminates the pressure differential that drives water through joints. Stick systems give you geometric flexibility at the cost of installation speed, while unitized systems dominate high-rise construction because factory assembly produces better quality control and faster installation. Every curtain wall has to accommodate inter-story drift from wind and seismic loads, and AAMA 501.4 is the racking test that verifies the system can survive code-mandated drift without breaking glass. Point-supported and double-skin facades are dramatic and useful for specific programs, but they are expensive, complex, and introduce maintenance risk that follows the building for decades. And face-sealed curtain walls, the kind that assume a perfect exterior seal, fail predictably over time, and the resulting water intrusion claims are highly defensible against the architect who specified them without proper rain screen detailing. Most architects do not realize that vapor retarder placement varies by climate zone, and getting it backward is one of the most common envelope failures in the country. Condensation forms when moist air contacts a surface at or below the dew point. Inside the assembly, that means the temperature gradient through the wall crosses the dew point of the air at some point in the section, and water condenses on whichever surface lives at that temperature. In a cold climate, the warm, moist interior air drives outward. The gradient cools as it moves out, and condensation lands on the sheathing if the vapor retarder isn't on the interior face. In a hot, humid climate, the moisture drive reverses. Hot outdoor air drives inward, and putting a vapor retarder on the interior face traps moisture against air-conditioned drywall. The wall rots quietly for years. Mold colonizes the cavity, and you receive a phone call from an attorney who has the assembly section you drew and a hygrothermal expert who can prove the failure was foreseeable. 4 climate types and the moisture control strategy each one demands. 4 climate types, 4 very different moisture control strategies, and the vapor retarder lives in a different place in each one. Cold climates in zones 5 through 8 move warm, moist interior air outward through the assembly. The strategy is to put a vapor retarder on the interior face, an air barrier on the exterior face, and enough continuous insulation outboard of the sheathing to keep the sheathing above the dew point. Hot, humid climates in zones 1 and 2A reverse the drive. Hot, moist outdoor air pushes inward, and an interior vapor retarder would trap that moisture against the cool drywall and ferment the cavity. The strategy there is to use an exterior air barrier, omit the interior retarder, and design the assembly to dry inward toward the air-conditioned space. Mixed climates in Zone 4 see both directions depending on season, so smart variable permeance retarders or all exterior insulation are the only safe approaches. And hot, dry climates in Zones 2B through 3B have minimal moisture concern, so the air barrier is the primary control layer and a vapor retarder is generally unnecessary. Cold climates have a precise math problem. What fraction of total R value must sit outside the sheathing? The cold climate detailing problem boils down to one number per climate zone, the minimum fraction of total R value that has to sit outboard of the sheathing to keep the sheathing temperature above the dew point. In climate zone 5, the threshold is 27%. In zone 6, it climbs to 36%. In zone 7, 43%. In zone 8, you need at least 50% of the wall's total R value outside the sheathing. If you fall below the threshold for the zone, the sheathing temperature drops below the dew point during the design heating event. Water condenses on the inside face of the sheathing, and the wall starts a slow rotting process that the owner won't notice until the gypsum face fails or the framing turns black. This is the most common cold climate envelope failure in the country, and it traces back to a designer who specified an aggressive cavity bat without enough continuous foam outboard. The architect ends up personally liable in the resulting professional negligence claim because the threshold is published, well-known, and easy to satisfy. Lock 4 takeaways before specifying the next wall assembly outside Climate Zone 3. 5 takeaways from condensation analysis. Vapor retarder placement varies by climate zone. There is no single rule that works everywhere, and applying a cold climate detail in a hot, humid climate is one of the most cited envelope failures in the post-loss literature. Cold climates demand an interior vapor retarder paired with enough continuous insulation outboard of the sheathing to keep the sheathing above the dew point. Hot, humid climates reverse the strategy. Omit the interior retarder, run the air barrier on the exterior, and let the assembly dry inward toward the air-conditioned space. The exterior insulation ratio rule for cold climates runs from 27% of total R value in Zone 5 up to 50% in Zone 8, and falling below the threshold guarantees internal condensation. And specifying the wrong face vapor retarder is documented professional negligence. The math is public, the failure mode is known, and the lawsuits land squarely on the architect who drew the section. Every architect should walk into design development knowing that the envelope is not certified by the drawings. It is certified by tests. Air leakage tests, water penetration tests, structural wind pressure tests, and whole building blower door tests are the only evidence a court will accept that the envelope you designed actually performs. ASHRAE 90.1 caps whole building air leakage at 0.4 of a cubic foot per minute per square foot at 75 pascals, tested by ASTME 779. In many jurisdictions, that test is the deciding factor between code compliance and a failed inspection. Specify the tests in the project manual. Run them early enough in construction to repair before the envelope is concealed, and you have evidence. Skip the tests, hope the envelope works, and you've stamped a building whose performance you cannot defend when the water intrusion lawsuit lands. Pick the right test for the right phase, or the cost of remediation will fall personally on you. 7 test standards cover the 4 performance dimensions the envelope has to satisfy. 7 tests, grouped by what they measure and when they happen. Air leakage testing splits into 2. ASTME 283 runs in the laboratory on a window or wall specimen to demonstrate the product meets spec. And ASTME 783 runs in the field on the installed assembly to verify the contractor's work. Water penetration testing splits 3 ways. ASTME 331 applies static pressure in the lab. ASTME 547 cycles pressure dynamically for hurricane zone products, and ASTME 1105 tests the installed wall in the field. That field test is the definitive evidence in any water intrusion dispute. ASTME 330 is the lab structural capacity test, applying wind pressure to measure deflection and find the breaking point. And ASTME 779 is the whole building blower door test that pressurizes or depressurizes the completed building to measure total air leakage. The project specification must call out which tests apply, when they happen, and what the pass criteria are. 5 operational best practices separate the envelopes that pass from the ones that don't. 5 operational practices that separate the projects whose envelopes pass from the ones whose envelopes embarrass everyone involved. First, specify mock-up testing for the critical assemblies before the contractor commits to full production. The cost of a single mocked-up bay is far less than the cost of redoing 2,000 bays after the field test fails. Second, run field tests early enough that the contractor can repair findings before finishes conceal the wall. The worst-case outcome is a leak found after move-in, because then every repair has to demolish finish work. Third, test the most challenging conditions first: corners, transitions, penetrations, and parapet returns. The easy areas almost always pass. The assembly fails at the junctions, and testing those first lets you catch the system-level problem before it propagates. Fourth, plan for whole building blower door testing as standard practice, not as an option. The energy code is moving in that direction, and high-performance owners expect it. And fifth, run infrared thermography during commissioning to find thermal bridges and air leak paths non-destructively before you sign off. Lock 4 takeaways before specifying the next envelope mockup. 5 takeaways from envelope performance testing. The envelope is certified by the tests, not by the drawings, and the project specification has to call out the right standard for each dimension the assembly has to satisfy. Air, water, structural, and whole building performance each have an ASTM standard, and there are separate lab and field tests for the first two, because lab certification of a product does not prove the field installation works. ASTM E1105 is the definitive field water test, and it is the evidence used in any water intrusion dispute that lands in court. ASHRAE 90.1 caps whole building air leakage at 0.4 of a cubic foot per minute per square foot at 75 pascals, tested by E779, and that test is becoming code mandatory in a growing number of jurisdictions. And the operational rule is to test the corners, transitions, and penetrations first. That's where envelopes actually fail, and catching the failure mode there saves the rest of the building from the same defect. Most architects working on a net zero project for the first time assume the strategy is solar panels. That is the most expensive misread on the project. A net zero energy building, abbreviated NZEB, produces as much renewable energy on-site as it consumes over a year. The math forces a particular sequence. You cannot generate your way to zero because the roof area on a typical building is nowhere near enough photovoltaic capacity to balance the building's load if the load is anywhere near typical. The math forces you to reduce demand by 50 to 70% first, through envelope, through efficient systems, through passive design, and then generate the remainder on site. Skip the demand reduction work, slap photovoltaics on the roof, and you've delivered a building that pretends to be net zero on a marketing flyer while costing the owner twice what a properly sequenced project would have cost. The owner files lawsuits when the actual energy bills come in, and you cannot defend the design. 5 steps in priority order, and the order is the entire concept. 5 steps, and the priority order is the entire net zero concept. Step 1 is reducing demand by optimizing the envelope, insulation, glazing performance, and air tightness, and by cutting plug loads through equipment specification. The lowest energy kilowatt hour is the one the building never consumes. Step 2 is maximizing passive strategies. Orient the building for solar gain in heating climates or solar avoidance in cooling climates. Design for daylighting that reduces electric lighting demand. Plan for natural ventilation where the climate supports it, and use thermal mass to dampen swings. Step 3 is specifying efficient active systems: heat pumps, LED lighting, energy recovery ventilation, variable frequency drives, and high-efficiency HVAC to carry the remaining demand at minimum energy. Step 4 is generating renewable energy on-site, almost always with solar photovoltaics. And step 5 is monitoring and verifying performance through submetering, continuous commissioning, and occupant engagement. Without verification, the building drifts off its design point within 2 years. EUI targets vary by building type. The math shows which programs are easy and which are nearly impossible. 5 building types and the EUI math behind each one. Energy use intensity is measured in kilo BTUs per square foot per year, and it is the single number that decides whether net zero is achievable on a given project. Offices typically run 80 to 120, and the net zero target sits at 25 to 35, a 50 to 70% reduction that is achievable with disciplined design. Schools start lower, around 60 to 90, and target 20 to 30. Their lower occupied hours make them strong net zero candidates. Retail runs 70 to 110 and targets 25 to 35, the same band as offices. Hospitals are the exception. Typical performance runs 200 to 350. The operational requirements for ventilation, sterilization, and 24-hour HVAC don't compress, and net zero is very difficult to achieve on any honest accounting. Multifamily residential at 50 to 80 targets 15 to 25, and the consistent occupancy makes the model tractable. Pick the wrong target for the building type, and you'll be defending an overpromise to the client. Lock 4 takeaways before promising net zero on the next project. 5 takeaways from net zero energy. The order of operations is non-negotiable. Reduce demand first through envelope, then through passive strategies, then through efficient systems, then generate the remainder on site, then verify performance. You cannot generate your way to zero because typical buildings need 50 to 70% demand reduction before photovoltaic capacity is adequate, and the roof area on most projects is the binding constraint. EUI targets vary sharply by program. Offices, schools, and retail are tractable. Multifamily residential is achievable, and hospitals at 200 to 350 kilo BTUs per square foot per year are essentially impossible without operational compromises that owners won't accept. Be honest with clients about which buildings can hit the target and which cannot. Overpromising leads to the public relations failure and the lawsuits that destroy a firm's reputation. And post-occupancy monitoring is mandatory because buildings drift off their design performance within 2 years without active management. Most architects still think about building carbon the way the industry thought about it 20 years ago. Operational carbon from energy use is the problem, and efficiency solutions handle it. That model is breaking down. As electric grids decarbonize and net zero designs reduce operational consumption, the embodied carbon in materials becomes the largest share of life cycle emissions. And embodied carbon is the architect's specification problem in a way operational carbon never was. Life cycle assessment, abbreviated LCA, is the standardized methodology that quantifies environmental impacts across the entire life of the building: material extraction, manufacturing, construction, operation, and end of life. The LEED rating system awards credits for whole building LCA, showing a 10% reduction in at least 3 impact categories. Owners are starting to write embodied carbon caps into project requirements, and the architect who cannot deliver on those caps loses the project to one who can. Get the spec wrong, and the lawsuit is the owner's failure to hit their own published commitments. Before anything else, one acronym does the heavy lifting in product comparison. The Environmental Product Declaration, abbreviated EPD, is the single document that makes comparison shopping for low-carbon materials possible. Without an EPD, every manufacturer's marketing claim is unverifiable. With an EPD, you have a standardized, third-party verified report covering global warming potential, ozone depletion, acidification, and a handful of other impact categories, all measured by the same methodology against the same boundaries. The governing standards are ISO 14025 and the European standard EN 15804, which is specific to construction products. The function is exactly analogous to the way an NFRC label tells you the thermal performance of a window. Every product in the category carries the same label, the methodology is fixed, and you can compare apples to apples. Specify EPDs in the project manual, demand them at submittal, and you'll get the embodied carbon visibility that hitting any whole building LCA target requires. Carbon comes in 3 flavors, and the share the architect controls is the largest one. 3 carbon categories and the trajectory each one is on. Operational carbon, the CO2 emitted from the energy used to operate the building over its life, historically represented 60 to 80% of life cycle emissions. As grids decarbonize and high-performance design reduces operational demand, that share is dropping fast. Embodied carbon is the CO2 emitted from material extraction, manufacturing, transportation, construction, and eventual demolition, historically 20 to 40%, and the share is rising as operational carbon falls. Upfront embodied carbon is the subset emitted before the building is occupied. Life cycle phases A1 through A5 in the European EN 15978 framework, and it is by far the largest piece of total embodied carbon. The reason this distinction matters is who controls each one. Operational carbon is controlled by the HVAC engineer and the energy code. Embodied carbon is controlled by the architect through material specification, and upfront embodied carbon is locked in by the time construction starts. The architect who knows how to read an EPD and choose low-carbon concrete, low-carbon steel, and biogenic carbon storage in mass timber has direct control over the biggest decarbonization driver in the industry. Lock 4 takeaways before the next material selection meeting. 5 takeaways from life cycle assessment and embodied carbon. The trajectory has flipped. Operational carbon, historically the dominant share, is dropping as grids decarbonize, and embodied carbon is the increasing share of total emissions, with upfront embodied being the largest subcategory. Embodied carbon is the architect's lever because it is set by material specification, and upfront embodied is locked in before construction completes. Life cycle assessment quantifies impacts across the entire life of the building under ISO 14040 and 14044, and tools like Tally, One-Click LCA, and Athena make whole building LCA practical at design stage decisions. Environmental product declarations are the standardized, third-party verified product reports that let you compare materials head-to-head. Demand them in the project manual and at submittal review. Concrete and steel account for the majority of embodied carbon in most buildings, so start there with low-carbon mixes, reduced cement content, and mass timber substitutions where structure permits. And the LEED rating system rewards whole building LCA, showing a 10% reduction in at least 3 impact categories. That credit is the gateway for projects committed to whole building decarbonization. Every architect who has chased a LEED Platinum certification understands the mechanics. Collect enough points across enough categories and trade off the items that don't suit the project. That logic does not survive the Living Building Challenge. The Living Building Challenge is performance-based. It organizes requirements into 7 petals, each containing mandatory imperatives, and every imperative within an attempted petal must be met. There are no shortcuts and no trade-offs. The certification only issues after 12 months of measured operational performance. Not a design model, not a calculation, the actual building performing in the real world. Most architects who promise a living building deliver something less, and the resulting lawsuits over breached marketing commitments have hit firms hard. The exam will test whether you understand the difference between LEED's point trading and LBC's all-or-nothing structure, and whether you can match the certification to the owner's tolerance for failure. The Living Building Challenge organizes itself around 7 petals. The structure deserves a careful look. Living Building Challenge organizes itself into 7 petals: place, water, energy, health and happiness, materials, equity, and beauty. And each petal contains a set of mandatory imperatives. The structure is the entire point. Where LEED lets you assemble enough scattered points to certify, LBC requires that every imperative within any petal you attempt be fully met, with no substitution, no equivalent, and no design team workaround. The place pedal alone bans development on previously undeveloped greenfield sites, mandates urban agriculture, and requires habitat exchange. 3 imperatives that on their own kill most suburban projects. The materials pedal includes a red list of banned toxic compounds, including formaldehyde, PVC, and 100+ other substances, and every product in the building has to pass that list. Energy requires net positive performance. The building must produce more energy than it consumes over a 12-month measurement period. And every certification is issued only after 12 months of actual measured performance, not a calculation, not a model, real operating data. 3 high-performance certifications cover the same conceptual ground from very different angles. 3 high-performance certifications, 3 very different approaches to the same goal. LEED Platinum is points-based, allows trade-offs, requires roughly 50% better energy performance than code, mandates a 40% indoor water reduction, and verifies through documentation review. It is achievable for most committed projects and is the dominant certification in U.S. markets. Living Building Challenge is performance-based and brutal. Every imperative within an attempted pedal must be met. Energy must be net positive. The building produces more than it consumes. Water must be net positive. The building captures all water it needs. Materials must clear the red list of banned toxic compounds, and verification requires 12 months of actual operating performance data. Few projects certify because the bar is genuinely difficult and the cost premium is real. Passive House is energy-focused and strict. A 60 to 90% reduction in heating and cooling energy, verified by blower door testing and energy modeling against the PHPP calculation tool. The Passive House standard does not address water or materials directly. It is a narrowly scoped, deeply verified energy certification. Lock 4 takeaways before committing the project to any certification. 5 takeaways from high-performance certifications. LEED is points-based, allows trade-offs across categories, and is achievable for most projects committed to better-than-code performance. The Living Building Challenge is performance-based and requires every imperative within every attempted pedal to be fully met. No equivalence, no trade-offs, no design stage workarounds. Passive House is narrowly scoped to energy performance, demanding a 60 to 90% reduction in heating and cooling energy verified by blower door testing and the PHPP calculation tool. It does not address water or materials. Only the Living Building Challenge requires 12 months of actual measured operating data before certification issues. The others certify on documentation or design stage modeling. And promising LBC certification to an owner who does not understand the all-or-nothing structure is a documented professional negligence pattern. When the building falls short and the certification fails, the architect ends up personally liable on the breached commitment. Most architects start material selection with aesthetics and learn the hard way that the structural engineer, the code official, and the embodied carbon analyst have very different priorities. Tension-critical applications, long-span beams, hangers, ties, demand steel. Mass-critical applications, vibration control, sound isolation, thermal flywheel, favor concrete or masonry. Carbon-critical applications favor wood or mass timber. Schedule-critical applications favor prefabricated steel or unitized panels. The decision is multi-axis. The trade-offs cross fire resistance, embodied carbon, durability, and the IBC construction type the building can claim. And the architect who specifies a material without checking all 4 axes gets to redesign in design development when the code official rejects the type or the embodied carbon target blows past the cap. You'll be the one personally liable when the rework cost lands on the schedule. 6 common structural materials and what each one does under fire. 6 structural materials, 6 different fire stories, and the construction type the building can claim follows directly from the fire performance. Concrete has excellent inherent fire resistance because it is non-combustible and has high thermal mass. The rating method is the thickness of cover over the rebar, and the material satisfies the strictest IBC construction types 1 and 2. Steel is the opposite. It loses strength at roughly 1,000 degrees Fahrenheit, so unprotected steel is unsafe in any major fire. Applied fireproofing, spray-on cementitious, board, or intumescent paint restores the rating and lets steel qualify for types 1 and 2. Heavy timber and mass timber both perform better than their reputation suggests. Timber chars predictably from the outside in. The char layer insulates the structural core, and the National Design Specification provides charring rate calculations that allow the design fire to be modeled accurately. Light wood frame, by contrast, has thin, combustible members that fail quickly, so it is restricted to Type 5 construction. And masonry is the most fire-tolerant material the industry uses. Non-combustible, very high mass, and rated by wall thickness directly out of the code tables. Sustainability adds a second axis. Embodied carbon, recyclability, and renewability all enter the trade-off. 5 materials and the sustainability picture each one carries. Steel is high embodied carbon at production, but the industry is reducing the number through scrap-based electric arc furnace mills, and the material is 98% recyclable when the building eventually comes down. Most steel in U.S. construction today has substantial recycled content. Concrete is very high embodied carbon, driven almost entirely by cement production, and recycling is limited to using crushed concrete as aggregate. Low-carbon concrete mixes that substitute slag or fly ash for cement are the most impactful single specification change available to the architect. Wood is low-embodied carbon and actually sequesters atmospheric carbon during tree growth, but durability is moderate because wood needs protection from moisture and insects over the life of the building. Masonry sits in the middle. Moderate embodied carbon, limited recyclability, but excellent durability that often exceeds a century. Aluminum is very high embodied carbon, but highly recyclable and corrosion resistant. The secondary aluminum supply from recycling carries only a fraction of the carbon footprint of primary production. Lock 4 takeaways before the next material selection meeting on a code-sensitive project. 5 takeaways from material properties. Selection trades across 4 axes at once: fire resistance, embodied carbon, durability, and the IBC construction type the building can claim. And ignoring any axis sends you back to design development when the code official, the carbon analyst, or the structural engineer pushes back. Concrete and masonry deliver excellent fire performance and durability and qualify for the strictest IBC types 1 and 2 without applied fireproofing. Steel qualifies for the same types, but requires applied fireproofing, spray, board, or intumescent paint to satisfy the rating, and you specify the thickness on the drawings. Heavy timber and mass timber under the 2021 IBC qualify as Type 4 with subtypes A, B, and C, with charring rate calculations from the NDS providing the fire design basis. Wood is the only structural material that sequesters atmospheric carbon, while concrete cement is the largest single source of embodied carbon in most projects. And substituting slag or fly ash for a fraction of the cement is the most impactful single specification change available to any architect serious about hitting an embodied carbon target. Most architects treat specifications as paperwork they hand off to the spec writer. That misread is what loses construction defect lawsuits. Specifications are legally binding contract documents that complement the drawings. Drawings show quantity and location. Specifications define the quality, performance, and workmanship the contractor is bound to deliver. When a contractor delivers a product that fails, the question in court is whether the specification was clear, defensible, and consistent with industry practice. The CSI MasterFormat organizes the entire specification into 50 divisions, with a numbering system you'll see on every commercial project in the US. And the choice between prescriptive, performance, proprietary, and reference standard specification types determines who carries the performance risk: you, the contractor, or the manufacturer. Pick the wrong type for the situation, and you've shifted the liability to yourself. The lawsuit that follows is highly defensible against the architect. 11 of the most used CSI MasterFormat divisions and what each one contains. 8 divisions from the CSI MasterFormat that show up on virtually every commercial project, and the architect should know each of them cold. Division 00 is Procurement and Contracting, covering bidding requirements, the contract itself, and bonds. Division 01 is General Requirements, the catch-all for summary, submittals, quality control, and temporary facilities, and it sets the rules every other division operates under. Division 03 is Concrete, splitting into cast-in-place, precast, and reinforcement. Division 05 is Metals, covering structural steel, metal decking, and miscellaneous fabrications. Division 07 is Thermal and Moisture Protection, the home of insulation, waterproofing, roofing, and sealants. Division 08 is Openings, doors, windows, curtain walls, and hardware. Division 09 is Finishes, covering gypsum board, tile, flooring, and painting. Division 23 is HVAC, the home of all mechanical systems. The remaining 42 divisions cover the rest of the building, but these 8 are where the architect spends the most time during specification production. Within any division, specification language can take 4 very different forms, and each one shifts liability differently. 4 specification types, 4 very different risk allocations, and the architect's choice decides who pays when the product underperforms. The prescriptive specification names a specific product or standard. For example, 3M5200 Marine Adhesive Sealant. The architect warrants that the named product will perform, which is fine when the product has documented performance history, but exposes the architect when the product fails. The performance specification states the required outcome without naming the means. For example, the sealant shall maintain a watertight seal for 20 years under UV exposure, and the contractor carries the risk of delivering on that outcome. The performance approach encourages innovation and shifts liability to the contractor and product manufacturer, but it requires the architect to write a defensible performance criterion. The proprietary specification names one manufacturer and explicitly bars substitution. Use sparingly because it concentrates risk on the architect to defend the sole source. The reference standard specification cites an industry test method like ASTM C920 Type S, Grade NS, Class 25, and shifts a portion of the risk to the standards body that wrote the test. Lock 4 takeaways before writing the next specification division. 5 takeaways from CSI, MasterFormat, and specification types. Specifications are legally binding contract documents. Drawings show quantity and location. Specifications carry the quality, performance, and workmanship requirements the contractor is bound to deliver. The CSI MasterFormat organizes the entire specification into 50 numbered divisions, and the architect lives in roughly 8 of them on most projects: procurement, general requirements, concrete, metals, thermal and moisture, openings, finishes, and HVAC. Prescriptive specifications name a specific product or standard and put performance risk on the architect, because naming the product warrants its performance. Performance specifications state the required outcome without naming the means and shift the risk to the contractor and the product manufacturer to deliver on the outcome. And reference standard specifications cite established ASTM or industry test methods and anchor the specification in language a court will recognize, which is precisely what makes a specification defensible when the construction defect lawsuit lands. Ask any architect who has been through a budget meeting, and they'll tell you that value engineering is the most misused term in commercial construction. The legitimate definition is systematic. VE examines the function of each component, finds alternatives that deliver the same or better function at lower cost, and is conducted by a multidisciplinary team that includes the owner, the architect, the engineers, and the contractor. The illegitimate version of VE, which is what most owners and construction managers actually mean when they say it, is cost-cutting, simply stripping scope or quality until the budget closes, with no attention to whether function is preserved. Most architects who lose VE exercises did so because they accepted cost-cutting framed as VE, then watched the building underperform and absorb the lawsuits that followed. Constructability review is the parallel discipline that asks whether the design can actually be built efficiently and safely. A question worth asking before drawings are released, not after the contractor starts filing RFIs. The distinction between real VE and disguised cost-cutting plays out across 5 clean axes. True value engineering and disguised cost-cutting differ on 5 clean axes. The goal: true VE preserves the function while finding a lower cost path to deliver it. Cost-cutting lowers cost regardless of function impact. The process: true VE is a systematic analysis of function-cost relationships, walking through alternatives one by one. Cost-cutting just strips scope or quality with no analytical method. Timing: true VE happens in schematic design, when changes are cheap and the design freedom is maximum. Cost-cutting gets forced late in design development or construction documents after budget overruns surface, when changes are expensive and disruption is maximum. Example: the canonical true VE move is switching stone veneer to precast concrete with stone aggregate finish, similar appearance and similar function at substantially lower cost. The cost-cutting move is eliminating the stone entirely and substituting painted CMU, a totally different aesthetic and a different performance profile. And who? True VE brings the owner, architect, engineers, and contractor to the table together. Cost-cutting is usually a unilateral decision by the owner or construction manager that the architect learns about secondhand and ends up defending in court. Constructability review asks the parallel question: can the design actually be built? 6 constructability review questions every architect should run through before releasing drawings for bid. Can standard construction equipment access the site and the building? The wrong answer here forces specialty equipment and adds tens of thousands in unscheduled cost. Are the specified tolerances achievable with standard workmanship? Over-tight tolerances on fieldwork guarantee defects and RFI delays. Do the details account for the real-world construction sequence? Drawing a detail that requires assembly in an impossible order is one of the most common errors a court will use to prove negligence. Are there trade conflicts that will need field resolution? Every conflict the architect didn't catch becomes a change order that the contractor files against the project. Can materials be procured within the project schedule? Long lead items have to be flagged in design development so the owner can pre-order. And do the details allow for dimensional tolerances and thermal movement? Failing to allow for thermal expansion in a long facade is the kind of error that produces visible cracks and the lawsuits that destroy a firm's reputation. Lock 4 takeaways before the next VE meeting. 5 takeaways from value engineering and constructability. True VE preserves the function of every component while finding a lower cost path to deliver it, and the legitimate process is systematic, multidisciplinary, and conducted in schematic design when changes are cheap. Cost-cutting strips scope or quality without analysis, gets forced late in design development or construction documents, and produces the buildings that underperform and generate construction defect lawsuits. The VE team has to include the owner, the architect, the engineers, and the contractor at one table. Unilateral owner or construction manager decisions framed as VE almost always strip function the architect was warranting. Constructability review is the parallel discipline that asks whether the design can actually be built efficiently and safely. Running the checklist before drawings release catches build sequence errors that would otherwise surface as RFIs and change orders. And long lead items must be flagged in design development so the owner can pre-order. Failing that, the schedule slips on items the architect could have warned about months earlier. Every architect on a first major project has tried to select materials by aesthetic preference first and then backfill the technical requirements. That sequence fails, and you'll redesign in design development when the code official rejects the material's fire rating or the structural engineer rejects the spans. The framework that actually works is to establish the non-negotiable constraints first: code-mandated fire rating, structural capacity, exposure conditions, climate compatibility, and only then evaluate the remaining options against the soft criteria like aesthetics, sustainability, and cost. Material selection is a sequence, not a list. The exam will test whether you understand the order. The lawsuits trace back to architects who got the order wrong and warranted a material that fails the binding constraint, and the rework cost on a misspecified material can swallow a project's entire contingency. 8 criteria, in roughly the order that filters material options from many to few. 8 criteria the architect should walk through on any significant material decision. The first is structural performance. Does the material meet load, span, and deflection requirements? Higher performance materials almost always cost more. The second is fire resistance. Does the material meet the code-required rating, and is it inherently non-combustible, or does it need applied fireproofing? Non-combustible options are often heavier and more expensive. The third is durability. What is the expected service life? What maintenance is required? More durable materials carry a higher first cost but lower life cycle cost. The fourth is moisture resistance. Is the material appropriate for its exposure, and will it degrade in the presence of moisture? Resistant options are often less sustainable or aesthetically limited. The fifth is sustainability. Embodied carbon, EPD availability, recyclability, and local sourcing all factor in. Sustainable options may cost more or restrict the palette. The sixth is aesthetics. Does the material achieve the design intent? The best performing material is rarely the most aesthetic. The seventh is cost. First cost, installation cost, and lifecycle cost all matter. The lowest first cost rarely equals the lowest lifecycle cost. And the eighth is availability. Locally sourced, regional, with manageable lead time. Specialty materials add schedule risk that the client will hold the architect accountable for. The sequence in which these criteria get applied decides the outcome. 5 steps, applied in this order, deliver defensible material selections. Step 1 is locking the non-negotiable constraints: the code-mandated fire rating, the structural capacity, the weather exposure the assembly has to survive. These are constraints, not choices, and applying them first eliminates entire material categories that you would otherwise waste time evaluating. Step 2 is filtering the remaining candidates by performance: durability, moisture resistance, and any specific environmental tolerance the project demands. Step 3 is applying the sustainability criteria. Among the performance-qualified options, evaluate embodied carbon through EPDs, recycled content, biogenic carbon storage, and local sourcing. Step 4 is testing the shortlist against cost and aesthetics. Life cycle cost matters more than first cost on long-life buildings, and aesthetic fit decides among materials that satisfy everything above it. And step 5 is verifying availability, confirming lead time and regional sourcing before the spec is finalized, because late discovery substitutions in construction are how budgets fail and lawsuits start. Lock 4 takeaways before the next selection meeting. 5 takeaways from the material selection framework. The order matters more than the list. Locking non-negotiable constraints first eliminates entire material categories that would otherwise consume design team time, and applying performance filters before sustainability and aesthetic filters keeps the process defensible. The 8 criteria, structural, fire, durability, moisture, sustainability, aesthetics, cost, and availability, filter the universe of available materials down to a short list the team can actually choose among. Sustainability has moved from an end-of-process check to an early filter as embodied carbon targets become contractual. Specify EPD-backed materials early, or you'll redesign for the carbon cap later. Lifecycle cost almost always beats first cost on long-life buildings, and the architect should be the one making that case to the owner when VE meetings try to strip durability. And verifying availability before the spec is finalized prevents the late discovery substitution that kills schedules and starts the lawsuits over delayed delivery. Most architects treat fire protection as something the MEP engineer specifies and the architect routes around. That's exactly the wrong posture. Fire protection is a building system that has to integrate with the architecture, the structure, and the mechanical design from the earliest stages, and the choice of suppression, detection, and smoke control follows directly from the occupancy, the building height, the contents, and the owner's requirements. Pick a wet pipe sprinkler for a data center, and you've guaranteed that the next sprinkler accidentally tripped destroys 6 figures of server hardware. Pick a wet pipe for an unheated garage, and the system freezes, and the building loses its fire protection coverage. Pick a carbon dioxide system in an occupied space, and you've created a lethal hazard that has killed people in documented incidents. The architect commits to these choices in design development, and getting any of them wrong is documented professional negligence territory. 6 suppression systems, each tied to specific occupancies and hazards. 6 suppression systems, each pinned to a specific occupancy and hazard profile. Wet pipe sprinklers hold water in charged pipes. When a sprinkler head opens on heat, water flows immediately. They are the most reliable, the most economical, and the dominant choice for offices, residential, and retail, but not for unheated spaces where pipes can freeze. Dry pipe sprinklers hold compressed air in the pipes and admit water only after a head opens, which makes them right for unheated garages and loading docks, but slower in response. Pre-action systems charge the pipes only after an independent detection signal. That interlock prevents accidental discharge in data centers, museums, and telecom rooms where water would destroy the contents. Deluge systems use open heads that all discharge simultaneously, drenching the entire area on actuation. The right answer for aircraft hangars, high-hazard industrial, and transformer vaults. Clean agent systems use a gas suppressant like FM200 or Novec that leaves no residue, which is why they're specified for server rooms, archives, and electrical spaces. They require a sealed room, and they cost real money. And carbon dioxide systems suppress with CO2, which is lethal to occupants and has killed people in documented industrial incidents. They require pre-discharge alarms and occupant lockouts before any actuation. Detection runs in parallel, and the difference between conventional and addressable systems is enormous in service. Conventional and addressable fire alarm systems differ on 5 axes that the architect should know cold. Detection. Conventional systems identify only the zone where the alarm is occurring, which, on a large building, can leave the responder hunting through dozens of devices on a single floor. Addressable systems identify the exact device location, which, in a hospital or high-rise, can save the minutes that decide whether a fire stays small. Wiring. Conventional requires a separate circuit per zone, which gets expensive in complex buildings. Addressable systems run a single loop with many devices, dramatically reducing the wiring quantity. Cost. Conventional has a lower initial cost but higher life cycle because maintenance and code update modifications get expensive over time. Addressable has higher initial cost but lower life cycle. Best for conventional fits small buildings with few zones. Addressable is the standard for hospitals, high-rises, and large complex buildings where pinpoint identification matters operationally and legally. And the code trend has been toward addressable for over a decade. Many jurisdictions now mandate addressable for new construction above defined size thresholds. Lock 4 takeaways before the next fire protection coordination meeting. 5 takeaways from fire protection system selection. Suppression choice is driven by occupancy and hazard profile, not by uniform application. Wet pipe sprinklers dominate offices and residential. Pre-action protects data centers and museums where accidental water discharge would destroy the contents. And deluge systems handle aircraft hangars and high-hazard industrial. Clean agent suppression with FM200 or Novec protects contents from water damage, but requires a sealed room and substantial budget. Carbon dioxide suppression is lethal to building occupants and has killed people in documented industrial incidents. Pre-discharge alarms and occupant lockouts are mandatory and non-negotiable. Addressable fire alarm systems have become the new standard for new construction in most jurisdictions because they identify exact device location instead of just the zone. That pinpoint information saves response time and lives. And the entire fire protection design has to integrate with the architecture from schematic design forward. Bringing the fire protection engineer in during design development guarantees redesign work and the lawsuits that follow code-driven late changes. If you came into this module looking for a single right answer to each advanced systems question, you have read the practice wrong. There isn't one. Every decision you make here is a negotiation between 4 dials: first cost against operating cost, performance against schedule, schedule against constructability, and design ambition against any one of the other 3. And your job is to tune them deliberately, with the trade-off named on the record. Lateral system selection tunes stiffness against planning freedom. Curtain wall versus window wall tunes performance against first cost. Underfloor air tunes long-term flexibility against initial complexity. Commissioning tunes installed certainty against schedule. Embodied carbon tunes material familiarity against life cycle integrity. Spec type tunes risk allocation against procurement freedom. And value engineering tunes design intent against cost relief, with the timing of the conversation determining which way the dial moves. Hold the dials, name the trade, document the choice. That is the advanced practice on every project the architect runs. Structure and envelope hold the largest first cost dials, so start there. Lateral systems and curtain wall typology drive the largest swings before any other decision. 3 decisions drive the structure and envelope dials. Lateral system selection trades stiffness against planning freedom. Moment frames preserve open architecture by transferring lateral loads through beam column connections, but deflect more under load and demand careful drift control, while braced frames and shear walls deliver stiffness at the cost of placing the lateral elements where the architecture has to work around them. Seismic design category and the building's irregularities together drive the lateral force the structure has to absorb. An SDC of D or E in a high seismic zone with a re-entrant corner or a soft story can multiply the design force well past what a regular building in the same zone would see. And the architect's massing decisions shape that number before the engineer ever opens an analysis file. And the curtain wall versus window wall choice is the envelope typology fork. Curtain wall hangs from the slab edges as a continuous skin, performs better thermally and acoustically, and costs more. While window wall sits between slabs floor by floor, is simpler to install in repetitive residential applications, and costs less. MEP and performance hold the long-term operating dials. Different decisions, same trade-off discipline. 3 levers lock in the building's long-term operating and carbon profile. Underfloor air and chilled beams are higher performance alternatives to the default VAV system. They decouple ventilation from sensible cooling, deliver better thermal comfort, allow more reconfigurable floor plates, and reduce fan energy at the cost of higher first cost and more rigorous coordination during construction. Commissioning is the lever that trades schedule for installed performance certainty. Bringing a third-party commissioning agent onto the project adds calendar weeks for testing and documentation, but it converts the design intent into verified installed performance and catches integration errors that would otherwise show up as occupant complaints in year one. And embodied carbon is the lever the discipline has only recently learned to pull deliberately. Life cycle assessment quantifies the carbon embedded in the materials themselves, and on most projects, structure and envelope dominate the inventory. So material substitutions in those two layers move the needle far more than minor finish level choices. Specifications and value engineering close the arc, the documentation that converts design choices into procurable scope and allocated risk. 3 documentation levers govern how the design ends up procured. The CSI MasterFormat is the industry-standard 50-division structure that organizes specifications across every project type. Using it consistently lets contractors, subcontractors, and product representatives find the requirements they need without relearning the document. Specification type is the risk allocation lever. Descriptive specs tell the contractor exactly what to install and shift performance risk onto the architect. Performance specs state the outcome required and shift selection risk onto the contractor. And proprietary specs name a specific manufacturer and constrain pricing flexibility in exchange for design certainty. And value engineering is the most misused tool on the project. Done correctly, VE is an early phase conversation that protects design intent by identifying alternatives before commitments harden. But done incorrectly, it is a big day rescue operation that strips features after every party has already optimized around the original program. 4 takeaways close the advanced systems arc into the trade-off discipline that distinguishes a real project architect from a textbook one. The takeaway from the advanced systems arc is a discipline of named trade-offs, not a memorized inventory of correct answers. Lateral system selection is a stiffness against planning trade, and the architect's value is in articulating the trade rather than picking moment frames or braced frames as a default. High-performance MEP and commissioning together trade first-cost dollars for long-term certainty about energy use, thermal comfort, and verified installed performance. And the trade is defensible on projects where the owner carries the operating budget. Embodied carbon focuses the carbon question on structure and envelope, because those 2 layers dominate the inventory on most building types. That is where material substitutions actually move the number, and finish-level decisions move it marginally. And the procurement document pair closes the picture. Specification type is a risk allocation choice that has to match the delivery model the project is using, and value engineering only protects design intent when it happens early in the schedule, rather than at bid. Tune the dials with intention, document the choice. The advanced practice is the trade-off named on the record.